Suppose we have a charged particle in motion. Let us take two frame of reference. S, which is sitting on the charged particle, and another frame of reference S prime, which is observing the charged particle in motion. Now, let us see what the two frame of reference are observing. So, according to S frame of reference, the charged particle is at rest and it is seeing a non-zero electric field, and since the charged particle is at rest, the magnetic field will be 0. What about S prime? So according to this frame of reference, the charged particle is in motion and it will see a non-zero electric field as well as it will see a non-zero magnetic field. Now, both the frame of reference are observing the same system, but their set of observations are different. Why it is different? That is what we are going to find out in this video. Let us take an example. Suppose we have a wire here and the one end of the wire we will call it point P, and in the other end will create a disturbance. So this disturbance will take some time to reach at point P. So this time will be given by this expression where r is the distance and v is the velocity of the disturbance. If we take a similar analogy, let's say we have a point charge q and at point P the electric field generated by this point charge is E vector. Suppose if I displace the point charge. Let us denote the new electric field at point P by E prime vector. Now let us try to ask one question. How fast does the point P knows that the charge has moved? So the time it will take for the disturbance to be experienced at point P will be given by r by c, where c is the speed of light. Now whenever c shows up, there is a clue that something deeper is happening inside, and that is nothing but relativity is coming into picture. So we can say that the electromagnetic interaction happens at the speed of light with a delay. Since the relativity is coming into picture, this changes the whole game. Let us try to recap some concepts of relativity. In mechanics, whenever we have space, which is denoted by the x, y, z coordinate, if we want to observe some motion, then we take the time part separately. We do not combine space and time. But in relativity, the time and the space, they are not independent quantity, rather they are dependent quantity. So we'll have a space part and time part simultaneously. And we will be denoting each and every event by x, y, z and t. Here, the change in time depends on space and vice versa. Suppose we have a frame of reference S and we have another frame of reference S prime, and if S prime is moving with some velocity v and there is an event happening at point P. Now if we observe this event from S, we'll have x, y, z and t, but if we observe the same event happening at point P from S prime, we'll have another set of space-time coordinate. Now the relation between these two set of space prime coordinate, it is given by the Lorentz transformation. What will happen to electric field and magnetic field when we combine with relativity? So this E and B vector, they are field quantities. So what is a field? A field is a way to describe how a particle would feel a force depending on where it is. For example, if I take a positive charge, the electric field will be coming out from the point charge. So in order to calculate this electric field, I have to place a test charge. So this test charge will experience a force, and using this relation, we can calculate the electric field. Similarly, for magnetic field, we can take a current carrying wire So the magnetic field will be given by the right hand thumb rule. So I have to place a test charge and let it move with some velocity v. So, and using this relation, I can find out the magnetic field information. Here comes the interesting part. Generally, we describe electric field and magnetic field as separate entity, but in reality, it's a single entity. Let us try to find out more about this. Suppose you have a point P and you want to find out the electric field or magnetic field at this point. For that, you need two information. One is the field direction, another one is the test particle velocity direction. So we need two information at each and every point. Now we cannot use a scalar here because scalar gives only magnitude. We cannot even use a vector here because vector has a single direction and magnitude. So we need to go with tensor. And since we need two information here, so we can say that we need a two-rank tensor. And the two-rank tensor that represents as a single entity for the electric field and magnetic field, that is what we call as the electromagnetic field tensor. And in this video, we are going to represent this vector by f with two subscript mu and nu. The electromagnetic field tensor can be represented by using two indices, mu and nu. Now this mu and nu can have four different values. Here, 0 corresponds to the time part, 1, 2 and 3 corresponds to the space part. Since mu and nu can have four different values, this tensor can be represented by a 4 cross 4 matrix. Here is the matrix. Now, if you see these elements, the time and space part are included because if you see the indices, 0 is there and 1, 2 and 3 are also there. This we call it the space-time part. And the remaining 9 elements, they contain only the space part. So this we call it as the space-space part. Now this 4 cross 4 matrix, it has 16 elements, but the electric field and magnetic field, it consists of 6 elements, 3 from electric field and 3 from magnetic field. So this matrix has to be antisymmetry. This is the electromagnetic field tensor, and if you see carefully, the electric field components, they lie in the space-time part and the magnetic field in the space-space part. There is a physics behind this also, because electric field, it lives in the component where time mixes with space. This reflects the idea that electric field affects the acceleration of charge particle over time, whereas magnetic field components, they are purely spatial component. That is why the magnetic field affects only the particle direction without changing the speed. And in this representation, we can see that electric field and magnetic field are separately placed. But what happens if this field tensor is seen from another moving frame of reference? Suppose you have a frame of reference S and you have another frame of reference S prime, which is moving with a velocity v. Suppose we have a system here, and if you observe this system from S frame of reference, you'll be getting some information about the electric field and magnetic field. But if you switch the field, that is, you are observing from S prime frame of reference, then you'll get a new set of electric field and magnetic field. Now, the relation between these two set of fields will be given by the transformation of the electromagnetic field tensor. The electric field and magnetic field transformations relations, which you see in undergraduate textbooks, are derived from this tensor transformation. Now, when we are switching the frame of reference, the electric field and magnetic field components, which were initially separate, now gets mixes up. And because of this, electric field and magnetic field are not separate fields, rather it's a single field and it is called as the EM field tensor. In electrostatic and magnetostatic, nothing is moving near the speed of light. So is it possible that the mixing of electric field and magnetic field is not valid in these two cases? Like for example, I have taken this example and this is the case for electrostatic, so the charge is at rest. And the second example which I took here, the electric current is produced due to the electrons in motion, and electrons are traveling at a drift velocity which is very much less than speed of light. Now, even if the observer or the system is moving very slowly, the field interaction is happening at the speed of light with some delay. So the rules will still be governed by the relativistic rule. So here two factors are very important, and one is the field interaction and the other one is the relative motion between the observers. Because of these two factors, the mixing of electric field and magnetic field is still valid in electrostatic and magnetostatic. Thank you everyone for watching this video. Take care.